What is going on, everybody? It's your boy Average Leader here with another video, and today we are tackling number 1852, distinct numbers in each subarray. Now, this is a pretty new problem on Leetcode, so it hasn't been asked by a lot of companies this year at least, but I think it was a pretty good one to try out, and I think you guys can gain a lot from it. If you guys can go ahead and hit that subscribe and like button, that would mean the world to me. It helps my channel out a ton by giving it more exposure to people that don't know me. And if you want to see another problem done, just comment down below and I'll make sure to do it for you. And with that all out of the way, here we go. Given an integer array nums and an integer k, you are asked to construct the array ants of size n minus k plus 1, where ants of index I is the number of distinct numbers in the subarray. Nums at index I to I plus k minus 1 equals nums at index I. Okay, so as you can see, this is a very difficult problem to understand. So if I got this in an interview, I'd ask to see an example. And luckily Leetcode provides this example, which makes a ton more sense than the actual problem statement. So let's dive into this example. So we see that we are given this array of numbers, and for our output we get 3, 2, 2, 2, 3. And the question we got to ask ourselves is, how did we get from this input to this output? Well, in the explanation it says, okay, so the number of distinct elements in each subarray of size k is goes like this. So we're looking at each subarray of size 3, right? So in our first subarray of size 3, we have these 3 elements, 1, 2, 3. And there's 3 distinct elements in there, right? So that's why in our output array, we are going to put the number 3. Now, it looks like they're shifting over the array by 1. So we're going to index 1, 2, 3 now. And since there's only 2 distinct elements here, we see that there's a 2 in the next index. Now, after that, they shift over to 3, 2, 2. And once again, there's 2 distinct elements, so that's why they put a 2 here. And then after that, they shift over by 1. And once again, we have 2 distinct elements. We just have 2 and 1, so we put a 2 here. And finally, we shift over one last time to 2, 1, 3. And like we had in the first iteration, we have 3 distinct elements again, so we put a 3 in the last place of our output array. So it looks like our output array, like this calculation that they did up here, the output array has the size of n minus k plus 1. That looks like it's the number of iterations that we are going to do while we're doing this like weird shifting subarray kind of thing. So this makes a little bit more sense to me than the problem statement did. And if I was given this problem in an interview, the next thing that I would do, given the problem statement and an example, I'd ask the interviewer a few clarifying questions. So, I'd ask like, are we always going to have an input given to us? That's like a very easy question to ask. Like, will we ever have like a null value or like a empty array or something? But that's not very important for like our situation right now. Question that is important is, what is the range of our integers in our nums array? Okay. Like, are we going to have negative numbers? Are we going to have strictly positive numbers? And if we have negative or positive numbers, are we going to go to like positive infinity, negative infinity, or are we going to go to only like positive 50, negative 50? What's the situation? So let's just assume that we are only going to have positive numbers in our nums array, and the range is going to go to positive 1 to positive infinity. Okay, so with this information in mind, let's take a deeper look into this problem. So based off of what they're doing here, it looks like they're making this little window and they're just shifting or sliding the window over by 1 at each iteration. Do you guys know what this technique is called? Well, it is called the sliding window technique, and that's exactly what we're going to implement for this problem. And if you guys want to go see an example of a sliding window technique, you guys should go check out my maximum points you can obtain from cards video, which at the point of filming this video is Google's second most asked interview question. So go check that out and maybe come back to this one. But we know that this is a sliding window problem, and in a sliding window we will have 2 pointers. Okay, one at the start of our sliding window and one at the end of our sliding window. And we know that our window is going to have a range of k elements in it at all times. So like our first initial window, our start pointer would be at 0, at the 0th index, and then our end pointer would be at the second index, and this would represent all three of our elements in our window. And every time we slide over, I just move the start over by 1 to the to the first index, and then I'd move the end pointer over by 1 to this index, and we just kind of keep going down our array until we're at the end. So implementing a sliding window isn't too bad. The more interesting part of this problem is we need a way to find the distinct number of elements in each window, right? So that's going to be a little tricky. So let's think, how can we get the number of distinct elements in each window? Well, I guess a very brute force solution is for each window, we could iterate through each subarray like one more time and just count up the number of distinct elements somehow. So, like we iterate through these 3 elements, then once we shift our window, we iterate through these 3 elements, then once we shift our window, we iterate through these 3 elements. But, I think we can immediately see that this isn't the most efficient solution. Like we end up counting multiple numbers multiple times. Like for example, just in this iteration, we count 1, 2, 3, right? But then when I shift over, I'm going to count 2 and 3 again. And then when I shift over again, I'm going to count this 3 one more time. So it's not that efficient. We're like counting numbers that we've already seen before. So, that time complexity would like run in like, I think nk, O of n times k, where n represents the length of the nums and k represents each window. So that's not very efficient. So I guess the next thing that I think of is like, okay, what data structures could be used in this situation? So before we dive into the specific data structures, let's have a quick checklist of like, what is our data structure supposed to do? Well, 1, it's supposed to somehow hold the distinct number of elements of each window. 2, when we shift our sliding window, right before we shift, we need a way to remove this, like what our start pointer is currently pointing at before we increment the start pointer. So let's say we're at 1, 2, 3, our window is 1, 2, 3. Before we shift to 2, 3, 2, we need a way to remove our first element from the number of distinct elements that we're holding, right? And that leads me into the third thing. Right after we shift our window over, we need a way to add what our end is going to point to. So we need a way to do this efficiently, okay? So efficiency is always going to be the key when we're thinking about data structures. So now I'm going to list the top, the top data structures that I can think of off the top of my head. So off the bat, I think of array, array list, linked list, stack, queue, hash set, and hash map. Now, I'm going to go through each of these and pick out why I could use one or why I couldn't use one. Okay, so let's start with the array. I don't think this would be that useful because, with an array, we have a finite number of items. And since the range of each of our number of elements is, positive infinity, it's going to exceed, the number of spots that we're going to need in our array. And like, I think it's not that useful since we only have a finite number of items. And like, I just can't think of a way that we can use an array properly, knowing that we have an infinite range for each of our numbers. Okay, so that's very key. If we knew the range was going to be a little smaller, like only like up to 50 elements or something, maybe we could use an array. But since the interviewer told us that the range of each of the numbers is going to be like up to infinity, then maybe, it's going to be hard to use, okay? Okay, so that moves us over to the array list. Now, with an array list, let me think about this. In each iteration, we'd somehow like add the elements in our window into our array list. So I usually start with like a starting window, and I'd iterate through the first k elements. So I'd add 1, 2, and 3 into our array list. And then when I shift over, I could easily remove this 1, maybe by having like an index associated with it or something. And then I'd shift my whole window over, and then I'd add this 2. So adding and removing isn't necessarily the most efficient, right? So, but that's not the only problem. Let's say we put 1, 2, and 3 into our array list, right? Now, this first window isn't that bad. We're putting all 3 of these elements into our array list, and maybe what we could use to represent the distinct number of elements in our output array is at each index of our output array, let's just use the array list's size to represent the distinct number of elements. So since we have 3 elements in our array, we're gonna put 3 in our output array. Okay, that's fine. Now let's slide our window to the next window. So now we have 2, 3, 2. So we've removed this first one and we've added this this other 2. So in our array list, we have a 2, a 3, and a 2. And there lies the problem. Array lists take account for duplicates. Like it holds duplicates of any number. And in our case, if we were to use the size of the array list, we'd have a size of 3. But in our output array, we need a size of 2 in this situation, and I can't think of a way to not account for duplicates and not add and remove properly and all this other stuff. So I feel like an array list wouldn't work for our particular situation, and for the same reason, a linked list wouldn't work either, because once again, like you'd have to have if I shifted my window over one more time and I'd have this 2 already in my linked list, and I need to add this 2, it would be hard to count the distinct number of elements since it holds all duplicates. So a linked list wouldn't work either. Now moving on to stack and queue, stacks and queues are really useful for like when we have an ordering of sorts, right? Like a stack is used for a LIFO ordering, a last in, first out, and then a queue is used for a FIFO ordering, a first in, first out. So that those aren't really useful in our situation right now. But moving on to the hash set. Okay, so the hash set is interesting because it does hold the distinct number of elements. It doesn't hold duplicates. Okay, so let's think about this. Let me put the first 3 elements into our hash set. Okay, cool, I can do that, and I can use the hash set size to put into our output array. But then I'm going to remove this one and then shift over to the next window, right? And I'm going to add this 2. But in our hash set, there's only going to be, since we already have a 2 in there, we're not really going to add this duplicate 2. So there's only going to be 2 elements in our hash set, and this would be great because that's what we need right here. But notice this: when I shift the window one more time over, I'm going to remove this 2. Oh, well, actually, since I add this 2, it ends up evening out. Let me show you this window. Now, when I have this window, okay, right before, like I currently have 1, 2, and 1, 1 in my hash set, right? But now there's 2 2s in this window. And this is going to be important when we shift our window to the next one, okay? So now I'm going to remove this 2 from our hash set, and I'm going to shift my window over, and I'm going to add this 3 to our hash set. Now, let's think, what is currently in our hash set when I do this? There's 1, 1, and there's 1, 3. There's only 2 elements in our hash set, because when we remove this 2, since it doesn't kind of account for like the number of 2s that we have or the duplicates of the 2, it seems like we're removing all 2s from our window, even if there was like another one like we have right here. So since there's only 2 elements and we need 3 distinct elements in that last position, a hash set wouldn't really work. Okay, so for a hash set, it's cool. We can hold the distinct number of elements, but we can't remove properly. Now, that takes us to our last data structure that hopefully has a chance here. We're going to use the hash map. Now, similar to the hash set, it can hold a distinct number of elements, which is very good. It doesn't hold duplicates. That's very good. And let me think. Okay, so with a hash set, there's key value pairs that we put in, right? So if I were to maybe for the keys, put in like these numbers in our nums array, and maybe for the value, like usually I'll put like the count of each of our numbers in a hash map. That's kind of like what my mind is going towards right now. So let me just do that. I'm gonna start by putting 1, 2, 3 into my hash map, and I'm gonna put for each of these keys that I put, I'm gonna put a value of 1 since they only have 1 count each. Now, when I shift my hash map over, I'm going to decrement the count for this, and I'm going to shift over to these three elements, right? And when I add this 2 over, I'm just going to increment my count for the 2 key by 1, and I'm just going to keep doing this until I'm at the end of my array. So by doing this, we're basically solving that one problem that hash set was giving us. So if I had the same window here, in my hash map, in this current window, I'd have a key of 2 with a value of 2 and a key of 1 with a value of 1. Now, when I shift my window over to the next one, all I have to do To remove this first 2, all I'd have to do is decrement the count of the key 2 from our hash set, from our hash map. So instead of 2 with a value of 2, I'd have 2 with a value of 1 when I shift over, and then I just have to add this 3 with a value of 1 into my hash map, and once again, I just use the size of my hash map to represent the distinct number of elements, so I have 3 elements in there, and that's it. That's perfect. This is exactly what we need to do. I'm going to note, though, there is one important thing that we need to do with the hash map. So let's say we have these first 3 elements in our hash map, right? We have 1 with a value of 1, 2 with a value of 1, and 3 with a value of 1. When I shift my window over, I need to decrement the 1 in our hash map by a count of 1. Okay, so I basically need to make the key 1 have a value of 0 after I shift this over. Now, when I do that, we need to figure this out. Do I still want that 1 in our hash map? Okay, so let me think about this. Let's just assume I keep it in my hash map. I have a 1 with a value of 0, and then so it's going to be here, and then I'm going to shift my window over to 232. And since we have this other 2, I'm going to increment the value of the key 2 in our hash map. Okay, so before we had in this window, we had a key 2 with the value of 1, since there's only 1 count. But then when I shift over and I add and I take account of this 2, I'm going to have the key 2 with a value of 2 in my hash map. And I also have like the key 3 with a value of 1. Now, since I still have that 1 with a value of 0, there's 3 elements in our hash map. And since I'm using the size of my hash map to dictate how many distinct elements are in each subarray, I would have a size of 3 here. And that's not what we need in this index, don't we? We need we need a value of 2 in this position. So what I'm going to do, every time I decrement the count of a key and I hit 0 or something, if I hit a value of 0, I'm just going to remove that key value pair from my hash map. And if I were to do this, if I were to remove 1, that means I just have the key 2 with a value of 2 and the key 3 with a value of 1. So just 2 elements. And since I'm using the size and since there's only 2 elements, then this would work out properly for us. This would actually work for us. So, with all this in mind, it looks like the hash map is the way to go. And I'm basically going to implement everything that I've described in the code that I'm about to code out. The last tip I want to give you guys before I go and start this code is there's something really, really interesting that a hash map and hash set can do. Now, I don't know if this is a causation, but there is definitely like a high correlation with what I'm about to say. So, do you remember in our very first brute force solution that we did like some time ago, where I said, oh, let's just iterate through each of our windows and somehow count up like the number of distinct elements, right? So we'd basically have like a 1 for loop that would iterate through the entirety of our nums array, and then we'd have like an inner for loop that would go through each of these windows, right? A quick tip is if we ever have like an inner for loop that's usually causing the inefficiency, we can sometimes replace that inner for loop with either a hash set or a hash map. There's usually like a high correlation with like an inner for loop being replaced with a hash map or a hash set, and that's exactly what we ended up doing here at the very end of like, trying to find the pros and cons of each of our data structures. So, that's a little tip for you guys. Maybe if we knew that we had that inner for loop and we knew this trick, we can go straight to hash set, hash map instead of evaluating array, array list, linked list, and all the other data structures. So a little tip for y'all. That's kind of how toSum is done. And they take the inner for loop and they replace it with the hash set. So, okay, anyways, let's dive into the code. So the first thing I do when I do these problems is I always ask myself, what are we trying to return? In this case, we're trying to return an int array. So I'm going to have an int array here, and I'll call it answer equals new int. And what's going to be the size of the int array? Well, luckily, in the problem, they gave us the size because it says you are asked to construct the array ants of size n minus k plus 1. So I'm just going to copy this and put it right here, n minus k plus 1. Awesome. And the last thing we'll do is return this answer array. Okay, cool. Now I'm going to initialize the hash map that we are planning on using. Okay, so I'll have a hash map where the key is going to represent like the actual numbers that we're going to put in, and then the value is going to represent the counts of each of our numbers that we're going to put in. And I'm going to call this hash map counts equals new hash map. Okay, awesome. And next I will, initialize the pointers of our window. So I'll have my start pointer, which is going to hold the left boundary of our first window. So it's going to start at 0. And I'll have my end pointer, which is going to represent the right boundary of our window. So I'm going to make this k-1. And in this case, notice that I am keeping like an inclusive window here, where my start and end pointer are going to represent the very beginning of our window and the end of our window, but it's going to be inclusive, like it's including each of those numbers that it's pointing to. There are some sliding window problems where you might find it easier to use an exclusive window, but in my opinion, like 85% of the sliding window problems that I've done, I think it's easier to do an inclusive window like this. It's just easier to visualize for me, so that's why I'm doing it like this. Okay, cool. So the next thing I'm going to do, so we have our window here, right? Let's populate our hash map with our first window's distinct values, okay? So what I'm going to do is iterate through the first k elements, which is going to represent our initial window, and I'm going to put the counts of each of our numbers in the first k elements, okay? So for int I equals 0, I is less than k, I plus plus. And what I'll do is use the put method that's used to actually put elements into the hash map. So I'll do counts.put. And what am I putting in? Well, I'm putting in a key of each of these numbers, right? The actual like distinct value, I guess. Okay, so I'm putting in nums at index I. And what is going to be the value? It's going to be the count of each of these keys. Now, if I haven't seen a key before, right? Like for instance, if I were to put in these 3 elements into my hash map, I haven't seen any of these 3 elements in my hash map before. So I would put a value of 1 for each of these, right? But now I'm going to go down to example 2. Okay, now look at this. Our first 4 elements here are all 1s, and we're asked to have a k of 4, or like a window size of 4. So our initial window here would just be like all these 1s, right? In our hash map, I wouldn't want to have 1 with a value of 1. I want to have 1 with a value of 1 at this index, then 1 with a value of 2 at this index, then 1 with a value of 3 at this index, and then finally 1 with a value of 4 at this index when I'm basically done with iterating through my initial window, right? So I need a way to kind of like get what was currently in our hash map and then increment 1 to it. There is a really cool method that takes care of both of these cases, okay? And it's called get or default, which does exactly what it sounds like, okay? So if an element is already in our hash map, it's going to get that element, and I'm specifically getting like, this element right here. So if this element is a key that's already in our hash map, it's just going to get this, and we're going to add 1 to it, okay? Now, if an element isn't in our hash map, it's going to default to the number that I'm going to put right here. So it's going to default to 0, and it's going to add 1 to it. So this takes care of both cases that we're trying to tackle. If we've seen it already, it's going to get whatever value it currently holds, and it's going to increment it by 1. If it isn't in our hash map, it's going to default to 0, and it's going to add 1 to it. So that way, these 3 elements are going to have a value of 1 because it hasn't been seen yet. Okay, cool. So boom, look at that. We've initialized our boundaries for our window. We've put in the values. Excuse me. We put in the distinct values for our initial window, and now a sliding window. We end up iterating through the entire array. So I usually have another loop at this point. Okay, I'll usually have a while loop. And when do we want to stop? So let's think about this. So oh shit. Sorry guys. Sorry. Technical difficulties. I'm really sorry about that. That was my bad there. But okay, so when are we going to end our while loop? Okay, that's what I was getting to. Well, let's run a quick simulation here. So we're gonna have this window, And after we're done accounting for like the distinct number of elements in here, we're going to increment our start and end pointer. So we're going to get this window, then we're going to recount our distinct number of elements, then we're going to shift, then we're going to recount, then we're going to shift, then we're going to recount, and then we're going to shift one last time. We're going to recount, and we're done. Now notice our start pointer is here and our end pointer is here. So it looks like when the end pointer, which by the way, I hope you guys saw that, the start pointer was always at the beginning of our window and the end pointer was always at the end. I should have explained that. But here, notice that the end pointer is at the very end of our nums array, at least. So let's just keep iterating while the end pointer isn't at the end of our nums.length array. Okay, so what I'll do is while end is less than nums.length, okay, and inside of this while loop, we're just going to keep, strategically incrementing our start and end pointer until this condition is met. Okay, now the very first thing we need to do is, since we have our initial number of distinct elements in this hash map, the first thing we'll do is let's put that value into our answer array. So I'll say answer at an index of something, I'm going to leave it blank for a bit, equals counts.size. Now, what index are we going to use? So I want to show you guys one more thing. In that example, notice that the start pointer, in that last example, the start pointer was at this index right here, right? It was at the 0, 1, 2, 3, 4th index. Now at this 4th index, this window is going to represent the last position in our output array. And notice what index it's in. It's in the 0, 1, 2, 3, 4th index. So our start index actually is going to be a great representation. It's going to be a great tool that we're going to use, which is going to not only be the left boundary of our window at all times, but it's also going to be the index that we store the distinct number of elements in our output array. So I'm going to put the answer at the index of start, oops, if I can spell, is going to equal counts.size. So I'm initially going to take care of like the window that we tried so hard to, populate, right? And after this, what have we done? So after we count the number of distinct elements, the next thing we need to do is shift our start pointer up one. Okay, so we're basically shifting from a window of size 3 to a window of size 2 temporarily. Now, notice what happens here. I go from 1, 2, 3 to a window of 2, 3, and I'm, removing 1 from our window. So I need to remove 1 from our hash map. Okay, so that's gonna be the next thing that we do. Whatever our start pointer is currently pointing at, let's remove it from our hash map. So I'll do counts.put nums at index of start. So that's what our start pointer is pointing at. And all I'm going to do is counts.get nums start. So it's going to get the current value that that the key 1 has in our hash map. And I'm just going to decrement that value by 1. Okay. Now remember what I said earlier when I said okay, does it make sense if this value of 1 is 0? Like, should that still be in our hash map? No, we want to remove that. So let's do a quick check right after this. If the counts.get nums start equals 0, oh, did I do that right? Yep, equals 0, what are we going to want to do? We want to remove it from our hash map. So counts.remove nums start. Awesome. Okay, look at that. And then the last thing we got to do is increment our start pointer. So with these 3 lines of code, these a couple lines of code that we have here, we are basically taking care of us shifting our start pointer. So we're going from 1, 2, 3, and then we removed 1, then we incremented our start pointer. So now we just have a window of size 2, 3. Obviously, we need a window of size k. We only have a size 2 right now. So the last thing we need to do is increment our end pointer and then add that value that the end pointer is pointing at to our hash map. So I'm going to do end plus plus, and I will say counts.put nums at the index of n. So I'm putting this into our hash map, and just like we did before, when we initialized our initial window, right? If we've seen it before, then we're just going to want to get that value, and we're going to want to add 1 to that current value. If it hasn't seen it before, we want to default to 0, and then we're going to add 1 to it. So we're just going to place a value of 1 into our HashMap. So I'm actually going to copy this over here, and all I'm going to change is nums at index end is what we're looking for. Okay. And after this really takes care of our sliding window. This really does it. Now, the last thing that I'm going to want to ask you guys to do is whenever you guys are working with a sliding window problem, it is so important to double check to see if like the code that we have right now like works. Okay. And what I mean by this is, are we going to go out of bounds anywhere? You know, we're doing all this increments with specific pointers. We're specifically incrementing the start. We're specifically incrementing the end. We're accessing end and start multiple times. So we need to do one check, and let's just make sure that that we're not going out of bounds anywhere. Okay, so the only places we'd go out of bounds are at the beginning and at the end. Now I've done this example like with the beginning multiple times now, so I'm sure in the beginning it's fine. Let's just go through a quick run through of our code for the last few iterations of our code. Okay, and I think if you guys did this in front of your interviewer, like they would be hella impressed. Like they'd be so impressed. Okay, so if you recognize that with sliding windows we have the chance of going out of bounds in a few spots, we have a few edge cases that we might need to consider. They will definitely give you brownie points for that kind of stuff. So let's just assume that we're going to be on this iteration, okay, of where our window has 221, and I'm going to assume that my hash map is working properly, and I'm adding and removing from my hash map properly. So what happens here? Our hash map has 2 2s and 1 1, right? So the first thing that I do in my while loop is I put that size into the answer array at that start index. So I feel like that's going to work because 0, 1, 2, 3 is going to be at the third index. So 0, 1, 2, 3. It looks like there's 2 values, and in my hash map I trust that there's 2 distinct values in there, so that works fine. And then I remove it from my hash map. Then I do all this removal stuff, and then I increment my start index. So now I'm at this window. Okay, cool. Now the next thing I do is increment my end index. So I have 213, and then I add that 3 into my hash map. Now we need to go through this iteration one more time because if we don't do this, right, we're not going to actually put the size into that last placement of our output array, right? We're not going to have this 3 in there. So that's why we're going to go through one more time. Answer.index start is going to equal the counts.size. This is going to work for us. We're going to remove our initial index. That's fine. And then we're going to increment our start index. That's cool. Now this is where it is. This is where I want you guys to see. End plus plus. Okay, so we are basically going like out of the bounds of our nums array. This is fine. As long as we're not accessing nums at that out of bounds array, we shouldn't have a problem. But oh wait, look at this. At line 23, we're accessing nums at this out of bounds index, and we're accessing it like a few times here. So we're gonna get an array out of bounds exception, or error or whatever, right? So watch, I'm gonna run this code, and any data and oh boy. Oh, oops. Okay, well that's not the only thing that's wrong. Okay, so nums.length, not n. I'm sorry. So, and this is assuming that I have everything else right. So let's just hope that I don't make any other mistakes. Boom, array index out of bounds exception. Okay, so we see that we got this exception, right? So how can we actually fix this? Well, the problem is we need this line to execute one last time when we have this window right here, right? The problem is when we increment our end index out of the bounds, it's really this line that's causing all the problems. So let's just have a conditional here. Let's just say if end is less than nums.length, only then will we execute this line. Okay, so in this situation, when end was out of the bound, the integer that end was holding was 7, and the length of this array is 7, right? So even though it's out of bounds, since this conditional doesn't get executed, this line will never fire. So if I were to run this now, you see that? Boom, that works. Would you look at that? This is one way you could do it, okay? And before we move on, I'm just going to show you one other way we could. So clearly the problem happened when we went like one iteration one too many. You know what I mean? But we needed this line to execute, right? So what if we just went one iteration less, right? But now if we go one iteration less, that means that even though we're holding everything in this window, we're not actually executing one last iteration and firing this line. So in this place, in our output array, we'd have 0 because that's the default value that would be held in our integer array. And you see that happen. See, look at that, 0. So to combat this, what you could do is just copy this line and put it at the very end, one last line before you return. And oh boy, this kind of stuff bugs me. There we go. So if I were to run this should work out fine. So you guys, there's 2 options for you guys to pick. And there we go. So yeah, that works. Okay, now for me, I personally am going to use this conditional just because I like everything in a while loop, and this is how I thought of it when I first did this problem. So when I submit this, let's go ahead and see what we get.
They ask you how you are, you just have to say that you're fine. When you're
Oh my God. Oh, I'm so sorry. I also have to change the condition. That is my bad right there. And boom, look at that. Runtime 77 milliseconds, faster than 21.55%. Okay, so now on Leetcode, this doesn't look too great. But if your interviewer told you that you have an infinite range of numbers, this will work. Okay, this will get you past the round. If you explain it just the way I did and like add your little flair to it, you are going to kill that interview. Now, let's say after you do this, your interviewer gives you a follow-up. He or she tells you, okay, let's assume that the range of each of these numbers has a range of 100,000. Okay, so we can go from 1 to 100,000 as opposed to 1 to infinity. Okay, and that's actually what Leetcode has here. The constraint that it gives us is at each position, each position can be 1 to 10 to the 5th, aka 100,000. Okay, so that could be a follow-up that they give you, or at the very beginning of the interview, when you ask the interviewer, hey, like, what's the range of each of the numbers? They could tell you that, oh, we go from 1 to 100,000. Okay, now if that situation occurred, you can still use this code, right? And I feel like you would still be fine. Like I feel like you would still pass the interview. But let's just assume that they give you a follow-up. They say, hey, can you make this more efficient? Now you got to think, what's the thing that's causing the inefficiencies right now? Like this is pretty efficient code, mind you. Okay, this is pretty good, but we can make this more efficient. So, looking at our for loop, we iterate through like the first k elements here, and with our while loop, we just go through all the n elements. So our time complexity is O of n. We're not like double, triple, quadruple counting like we were doing before. The thing that I'll think of if I can't like change a while loop, if I can't like reduce the number of loops or something like that, is I would think to myself, okay, do I really need this data structure? Okay, and the reason I say that is because remember when we were evaluating our data structures, and the first data structure I said was, oh, we can't use an array because we have an infinite range for everything. But now the interviewer has given us a finite range that we can use for our numbers. And this is very crucial, important information for us to utilize, because if we are just using a hash map where the keys represent like the specific numbers and the value is just the counts of our keys, we can represent that entire thing utilizing just an array, okay? And the way we would do this is we would have an array, and I'll call this scene, okay? So scene equals new int, and the number of spots that our int array is going to hold is going to be all the numbers that could be represented, that could be in this nums array. So basically, if we had 3 spots here, I would just have an int array of size or of length 3. Well, actually, I guess in this case it would be length 4 because we're not zero indexing. Our first number starts at 1, right? So I'd have an int array of length 4, where each index represents the number in our nums array. All right, this is the equivalent to the keys in our hash map. And the value that each index is going to hold is going to be the counts of each of those numbers. So let's just say, once again, I'm going to have a simple example here. For this example number 1, we only have 1, 2, and 3. So I basically have an array of size of length 4. And when I initialize my first window, I would just have, at index 1, I'd place a value of 1. At index 2, value of 1. Index 3, value of 1. And before I shift my window, I just decrement what my start pointer is pointing to. So at index 1, I just decrement my value of 1 back to 0. And then I shift my window over. And then my end pointer is now pointing to this. So I would just increment the value of index 2 by 1, right? So index 2 before had a value of just 1. Now with this additional 2, it would have a value of 2, right? So I just keep doing that until I'm done with my nums array. So it's all the increments and decrements that we do in our hash map can be replaced with, the array equivalent. So kind of going back here, what is going to be the length of our int array? Well, since we are going up to 100,000 elements, 100,000 elements, and since we're indexing at 1, we're not zero indexing, I'm going to have my length be 100,001. Okay? And the reason, like I said, the reason we're doing the 1 is because we're not zero indexing here. So now all of the increments and decrements that we're doing, we can do the array equivalent. So here we're putting the nums of index I, and we're adding 1 to the current value or the current key. So all I would do here for the array equivalent is I do seen, and since the key is going to be the index of our array, I'd say seen at index of nums I plus plus. Okay, and I just increment 1, and now I don't need this line anymore, so I'm going to delete that. Okay, and where else am I decrementing or incrementing? Okay, I see here, counts.put nums at index start, and we're decrementing here. So all I would do in my seen array is I just do seen nums, and I do it at index start minus minus. So I'm decrementing there, right? So there we go. I'm removing that. And now the last place where we're incrementing or decrementing is right here. So once again, I would just do seen nums end plus plus. Now I can delete this line. So okay, we can add elements to our window, and we can delete elements from our window pretty quickly, pretty efficiently. The last thing we got to consider, and the real question becomes, how can I get the number of distinct elements using an array? Now, this one is a little hard to see in the beginning, but it can be done with an array. And I'll let you guys, if you guys don't know, I'll let you guys pause, think about it for a little bit, and unpause whenever you're ready. But in this situation, when we're using an array, let's think about when would we have a distinct element? Okay, so let's see this example right here. Now, before, at each of these indexes, right, at each of these indices of 1, 2, and 3, we had a value of 0. Now, after we add all these values into our array, they get a value of 1, right? So it looks like whenever we're adding an element and changing the value from a value of 0 to 1, that's when we get a cool new distinct element. And like we did with the hash map, anytime we decremented a value and we got 0, we removed it from our hash map. So in the same way here, if we were to decrement a value and it became 0, we basically need to subtract 1 from our total number of distinct elements that we have. So if you guys are somewhat following this method, we could represent the distinct number of elements using a temporary variable, and I'll just call this variable count. Okay, and I'll set it equal to 0 in the beginning. So all I'm going to do is when we're initializing our initial window, if seen at index of nums I, so basically if that number currently has a value of 0, right? then I'm going to increment our count. So when we're initializing our window, what does that mean? So here, right, we're looking at the value 1 in our array, right? It currently has a value of 0. Before we increment that value by 1, we're going to increment our count, which is going to hold the distinct number of values at each window. Okay, so our count is going to increment by 1. Then we're going to look at 2. And once again, since 2 has a value of 0 before we increment it, we're going to increment our count by 1. So that's also going to be, the count is going to be 2 now. And for the same reason for number 3 here, our count is going to be 3. Now let's contrast this with example number 2. Okay, here we have 4 ones in the beginning. So our initial window is going to be these 4 numbers, right? So on our first iteration, we look at this one. Now in our array, since we haven't added anything to it yet, right, the value of at index 1 is going to be 0. So before we increment it, we're going to check, hey, is the value 0? In this case it is, so we're going to increment our count to 1. Now I'm going to look at this one. Okay, so it's going to check, hey, is the value at index 1 0? Well, no, since we just incremented it by 1 in the previous iteration, it's currently at 1 right now, so I'm not going to add to the count variable, which is going to, once again, hold the distinct number of elements that we have. So it's basically going to skip this, and it's just going to keep incrementing our array. So this is a really cool way where we can keep account of all of our distinct elements. And just like we did in our hash map, when we removed an element completely from our hash map, we're going to do the same thing with our array and with our temporary variable. So all I'm going to say is if seen at the index of start, because since we're removing the start index or the value of the start index, all I'm going to do is at the index of that start index, if that value equals 0 after I decrement it, what am I going to want to do? I'm going to want to delete it or basically remove that value from the total number of distinct counts that we're looking at. So the way I would do that is I just say counts or count minus minus. Okay, I'm decrementing from my count. So by doing this, this is like a really nifty way of once again holding on to the number of distinct elements at each window. The last thing we'd have to do is, since we're holding on to the number of distinct elements using the count variable, I would just have to replace this counts.size line with count, and that's it. And this way I don't even need a hash map. And this is much more efficient than utilizing a hash map. Okay, so now let me run this, make sure I don't make any errors. Oh, okay, so we made a little error here. Let me see, did I forget to increment my count? Oh yeah, look at this, guys. I almost forgot, sorry about that. So here, after I increment my end pointer, I'm adding whatever my end pointer is pointing to my array. So before this, let me just do a quick check. Let me see if it's a distinct number that we're adding. Okay, so all I'm gonna do is if seen nums end equals 0, just like we did right up here, right? If it's 0, that means it's a distinct value. So before we increment that value, let's just increment our overall distinct number of values that we're holding, which is held in our count variable. And okay, I think that is the last piece I need for this problem. And boom! All right, look at that, accepted. Hopefully this is right. I'm gonna submit this now, and we're gonna notice something very cool. We notice that we are significantly faster than we were before by just swapping our hash map to just this array that we have right here. That is how we're gonna do this problem. And now let's talk about the time and space complexity. Okay, so with the sliding window technique, it's very efficient. We're actually doing this whole sliding window thing in O of n time complexity. And for space complexity, well, let's see, where am I allocating space? Well, it looks like I'm allocating extra storage for this scene array. Now, remember, when you're trying to calculate space complexity, you never include your return storage, okay? So I'm not even gonna look at this answer. But we're only really holding n elements, right? Like even though this is holding like 100,001 spots, right? We're not actually utilizing every one of those 100,001 spots in our like while we're going through our implementation here, we're only utilizing like what's in our like our nums array. And when I say what we're utilizing, I mean like we're only incrementing and decrementing the n spaces that are in our nums array. So for that reason, I believe that the space complexity is also O of n. But let me know what you guys think about that one, because I'm interested to see if anyone thinks it's an O of 1 space complexity, because we are only using like this. Like I don't know. I feel like it's O of n, but I feel like I've also seen situations where like I've held like the alphabet, like only 26 spots in the alphabet into space complexity, and that's technically O of 1 since we're not like changing anything. But yeah, I think it's O of n in this case though. But let me know what you guys think. And you know, that's how you do this problem, guys. Hopefully you guys found some value. Hopefully you guys learned how to do this sliding window thing with both a hash map and an array. There's a lot of things that we could have learned from this problem. And you know, just let me know what you enjoyed about it. Let me know if there's any other problem you'd like to see done. And as always, you know, always feel free to smash that like button, to smash that subscribe button, be a part of this family. You know, I'd really appreciate that. But you know, other than that, you guys have a great rest of the day, and I'll see you guys next time.